Hello, everyone, and welcome to another episode of Physics Chat. Physics Chat, as you know, is a show where we talk to real life scientists and ask them what it is like to being a modern day physicist. We talk about everything from their hobbies to how they are pushing forward the boundaries of science. But I couldn't do this alone. I am joined today by Fox and Sophie, our fantastic co-host. How are you?
I am good. I am sleepy after Monday morning, but I'm good.
Yeah, I'm feeling great too.
Perfect. And on today's show, we have the incredible Sravan Kumar, who is a postdoc at the ICG in Portsmouth. Hello, Sravan. How are you doing?
I'm good. Feeling very good today. So I understood something in physics today.
Nice. That's always a nice feeling.
Yeah.
So let's dive into the science then. Could you tell us about your research in one sentence, please?
That's very difficult to say, but one sentence, quantum gravity and all of that. So basically, I worry about gravity and quantum mechanics and search for places where both can affect and influence our understanding of universe.
Wow, that sounds incredibly theoretical, but also very cool. Like really interesting.
Oh, I just study everything in the universe.
Also observational as well.
Can you explain the history of your field and what are the key developments in the last century?
I think of course, in theoretical cosmology, I work in theoretical cosmology and theoretical astrophysics, black holes, quantum gravity, and also, most importantly, I care about observations. And in my opinion, the biggest development is idea of inflation, cosmic inflation, which was initiated by Alexei Starobinsky, Linde, Guth, Mukhanov, all these excellent scientists. Well, after 40 years, we have the crystal clear map of the cosmic microwave background, which has proved that our theoretical understanding is indeed correct and going in a right direction. I think for me, it's incredible. And of course, black holes, gravitational waves, and black hole image, which keep coming to me in my dreams, black hole image.
Of course, we have theory, but we have to have observations to prove that theory. That's the point. But yeah, you do quantum gravity. So let's maybe dive into the quantum side of that first. So could you tell us about quantum fields in curved spacetime? That's a lot of jargon and sounds very complicated. But can you explain what it is and why it's important, please?
If we look at the whole history of physics, what are the major successes we have? I mean, the quantum field theory in Minkowski spacetime, for example, standard model of particle physics, right? And the Higgs boson we've discovered in 2012. And again, I would like to emphasize here the power of theory is so much so that it has influenced policymakers to invest a lot of money to find the fundamental secrets of the universe, right? So we had a huge success in understanding particle physics, the three fundamental forces of nature, the strong, weak, electromagnetic, and the other force is gravity. And gravity, of course, explained by general relativity, but it poses a lot of challenges. We do not fully understand black holes. We do not, I mean, let's ask a theoretical question, right? All the standard model, what is standard model? It's all particles. Well, to go in a deeper level, if we go in a deeper level, they are all quantum fields in a Minkowski spacetime. Minkowski spacetime is flat spacetime, no curvature, nothing. So now you ask a simple question. Okay, what happens to my Higgs boson if it is on a curved spacetime? What happens to how the Higgs boson would behave near the horizon of the black hole? How the Higgs boson would have behaved during the expansion of the universe? These are all the legitimate questions, right? So how do you understand quantum fields in curved space-time? Then next, how they affect our understanding of the universe? These are two related questions. One is much more theoretical, conceptual, but the concepts are the core of the development. So indeed, if you think of inflationary expansion, which has led to the whole large-scale structures like cosmic microwave background. Whatever the fundamental field responsible for inflation must be quantum mechanical in nature to get all this large scale structure. So it played a huge role. We still need to understand what are the detailed quantum aspects of it, and black holes, Hawking radiation. Hawking has showed clearly why quantum mechanics and gravity are important at the horizon scale of the black holes.
Can you explain just basic beginner terms, like what actually are quantum fields?
Let's try to understand from quantum mechanical point of view. What is quantum mechanics? Quantum mechanics is description of microscopic world, right? Let's say you have electron. Electron is particle, but it has wave nature. It has jewel nature. And if you have electromagnetic wave, it has particle nature. It behaves like a photon, a packet of energy. And when do you need electromagnetic wave to have particle nature? Especially when the photon hits the electron in the metal and kicks out. So this is a photoelectric effect, right? And so all the interactions of fundamental particles, electron and photons, so they have particle and wave nature, both. What is quantum field? Now we have electromagnetic field, right? What is electromagnetic field? Classical electromagnetic field. It is basically the pulses of electric and magnetic fields, right? Now, how do you take a transition from electromagnetic theory to photon? Let's say if you want to explain, we have a phenomenon, you have a gamma ray. Gamma ray is electromagnetic wave. Gamma ray, in the presence of heavy nucleus, splits into electron and positron. Positron is the antiparticle of electron. How this process happen? So this happen, you can explain this by starting with fields, and then you quantize them. And the process of quantization is basically from the field, you go to that particle nature. And so you need both of this understanding to describe the microscopic world.
We have these theoretical quantum fields. We have space-time that is curved. How do you then go from these very theoretical things to observations we actually see?
There is a huge difference between the field of particle physics and cosmology and astrophysics. In particle physics, if you take the Large Hadron Collider, you have protons and antiprotons, and you take many of them and just smash them and get soup of all the high energy particles you get. But you can repeat the experiment by any number of times you want, because everything is in your hand. If you go to cosmology, you just observe the relics of what might have happened in the early universe. You just observe, and you cannot conclude anything without help of the theory. You need a robust theoretical calculation that predicts according to the laws of general relativity, according to the laws of quantum mechanics, and that gives a formula. And you take that formula, and then you do the data analysis and make simulations and ask how many simulations are matching with your theory. So this is extremely needed in the field of cosmology and astrophysics.
What kind of observations do you use?
Yes, so now we have cosmic microwave background, which is measured by the Planck satellite, WMAP, like 20 years ago. So all these satellites, they just observe this cosmic microwave background, right? Now, so to explain cosmic microwave background, you need some specific formulas that are derived from the theory, give it to the data analysis people, they plug in it and analyze the data, and then see if the theoretical prediction is matching with the data. And also theoretical prediction helps to analyze the data. So it helps as a guiding principle. And the same way it goes for black holes. We are not yet fully there to explore completely the microscopic physics of black holes, but we already observed gravitational waves, and surely how we observe gravitational waves, because general theory of relativity predicts so precisely. Now, what is the next goal? To see quantum effects at the horizon, which is what Hawking enlightened us. There will be quantum effects, and also understanding of photon rings around the black holes. which if we progress enough technologically and clearly probe these photon rings, there we will see quantum fields effect in curved spacetime, because around the black hole, the spacetime is curved. So that's where I would definitely expect there will be something. And of course, there is also another thing which is involving understanding of dark matter, which is a completely new thing. We do not know. So yeah, there's a lot of theoretical development is needed to really understand astrophysical data.
Yes, thank you. I think this is all super interesting, and also interesting to maybe focus a bit more on this topic of observations in of quantum fields in curved spacetime. So as you talked about, we have this Hawking radiation, which I think everyone believes is there and is a real prediction, or like a very solid prediction of the theory. However, we have not observed this. And there is the question of whether we will ever be able to observe this. So I want to ask you about this relation between observations and theory, because I know you find this very interesting. And I guess my question is, do you think that physics, which cannot be observed, even though it is solid prediction of the theory, is meaningful in any sense?
Well, short answer is that the theory has to predict something which has, it has to be so precise that it has to give a number. No one expected to detect gravitational waves when they were proposed. No one thought that black holes are really could exist in the universe. So, but they were found. Why? Because the theory, general theory of relativity, was so precise to give that prediction. And it is important to have theories that give precise predictions, no matter whether they can be observed with the current technology or not. If the prediction is strong enough, it will be strong enough to push the boundaries of technology and contribute to the human progress. So it's important in that sense.
Yeah, I like that answer. Totally agree.
I think it's really cool that, I often think that if something can't be observed, it's useless. But the way you've just worded it, as it might be observed in the future, but we don't have the technology just yet, it's quite like a challenging thing to think about. I appreciate that. I know you're passionate about science history. So I was wondering if you could tell me maybe what your favorite observation is that's confirmed a theory.
Well, I'm still in the mindset of cosmology, thinking in cosmology. Surely, I think the lambda CDM model. Lambda is called the cosmological constant. So currently in the universe, we see a lot of galaxies which are far away from us are speeding, accelerating away from us. They are moving very, 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 very fastly away, moving away from us. And normally, you understand, gravity is an attractive force, and so everything should come together. But then we see an opposite effect, and we don't understand what it is. So the effect can be explained by a constant in the Einstein general relativity, and physicists do not like constant. They always want some fundamental explanation for the constant, but we do not have a fundamental explanation for this constant. But the proposal of introducing a constant itself is a very interesting feat, because you see something completely defining your understanding of general relativity, and then just add a constant, everything can be explained. How cool idea is. And this is exactly called the dark energy, because the unknown force that is pushing away the galaxy clusters, which was found in 1998. All the physicists shocked. But would you be surprised if I tell you that people expected some effect should exist by just looking at the pre-existing data? So there is a paper by Stravinsky and Kaufman Kaufman and Stravinsky in 85, 12 years before the effect of dark energy was discovered. They said by looking at the galaxies, they understood that there will be cosmic microwave background, but the density fluctuations in the temperature fluctuations in the cosmic microwave background has to be very, very small, very, very tiny. But still, they understood that no, this cannot be explained without adding two elements in the theory of Einstein general relativity in 1985. The two elements were cosmological constant and cold dark matter. CDM corresponds to cold dark matter. It is invisible matter. We do not know it exists because it bends the light according to Einstein general relativity. But without even any idea, these two terms added to fit the data. I think this is an amazing feat. What a finest physicists they are to guess that even before it was completely found. I think for me, it's unbelievable.
It sounds like these galaxy data that fit the Landor CDM model is your favorite?
It is my favorite, but surely we need to understand what lambda and CDM are, and they pose a very big challenge. And it is favorite because they pose a challenge. They explain and pose a challenge.
So maybe when they find that one day, that will become your new favorite observation, perhaps.
Yes, surely. And also I expect more challenges so that we can all work on. Yeah. There is another thing which is extremely remarkable from the other direction. That means some observation led motivated theoreticians to discover completely unknown objects. The first solution to Einstein's general relativity was found in 1916 by Schwarzschild. When Einstein's general relativity was proposed in 1915, and Einstein thought no one can solve the equations exactly. 3 months later, Schwarzschild, who is an astronomer, understood the very complex Einstein general relativity, and he solved it, and he was the first one to predict there should be black holes in the universe. After 30 or 40 years, maybe, so it's uncertain, I don't remember the years, it's Roy Kerr. You know how he came to the idea of rotating black holes? Like if you take Earth, rotates, Sun, all the stars rotate around. But so far, before Roy Kerr, no one even thought of black holes rotating. And Kerr came to the idea of after the discovery of pulsars, those fast rotating neutron stars. Then he thought of, why not black holes rotate? And he made the history. And today we see all the black holes in the universe are rotating. But he came to the idea by observation, from observations. This dialogue between observation and theory is what leads to new progress in physics.
Very cool. Yeah, thanks. Wow, thanks. Yeah, that was very interesting. So now, as part of Physics Chat, we also have some section where we ask the guests some question unrelated to physics or science, just for fun. And for you, I have the following. Where would a man go to get a good mango? Chris, because Chris told us that you maybe have a secret related to mangoes in Portsmouth. So if you want to reveal that secret, this is your space.
Okay. Well, the first suggestion is go to India, go to my place in India in the south, where you can get mango from the mango tree. And if the mango is completely ready from the tree itself, that would be the most tastiest mango you'll have in your life. And my place, my hometown in India would produce very tasty mangoes. Luckily, in UK, I was so surprised to find mangoes around, and there are some websites actually they bring mangoes from my hometown and make it available to people here. So I don't know in Portsmouth, but in Bristol they do exist. There are if you actually type Indian mangoes. You do get some websites offering that they take from the farms directly here.
I will be running to go get these mangoes.
Yeah, well, now the season is over. Maybe next year I will get the mangoes and we will all enjoy in Portsmouth.
Yeah.
Yeah.
So recently in Portsmouth, you organized this huge international conference, people from all over the world. Yeah, how was it? What was it like organizing such a big conference? Would you do it again?
So, well, of course, yes, I would love to do again. And one thing which I love about this conference, it happened thanks to all the people in Portsmouth, and with all help, we could bring together all people working in different fields in one conference, starting from quantum gravity to astrophysics, cosmology. Maybe we didn't touch stellar physics, but we touched everything, gravitational waves. So I think it was a lot of exercise. So like selecting the invited speakers and thinking about topic, and also covering the wide spectrum of universities from far away. We had people coming from Japan and US. So in my opinion, I think these are the kind of conferences should happen, which would bridge observations and theory and lead to new discoveries. So personally, I learned a lot.
Maybe you can organize the next one then.
Yeah, yeah, sure. I'll be very happy to.
Yeah, I don't really do theory in my PhD, but I went to a lot of the theory lectures about like rescalarization of black holes, and when we measure things in general relativity effects, are we actually measuring those, or are we measuring something else? Yeah, it was really interesting, and got to learn a lot of other bits of cosmology that I wouldn't necessarily learn in my PhD. It was very cool.
And I saw Sergi made a very beautiful poster.
Yeah, we can show the poster here. It is beautiful art.
Not necessary, yeah.
Yeah, do it.
It was definitely a lot of fun, the conference, and yeah, I enjoyed it a lot personally. But yeah, thank you so much, Sravan, for being on Physics Chat today. It has been genuinely interesting to learn about the puzzles in physics that fascinate you and a lot of more people. But yeah, this is it for today. And from everyone at the Field of View team, we hope you have a very good day, and goodbye.
Bye-bye. Thank you very much, guys. I really enjoyed all the questions and sharing and discussing these topics with you. Thank you.
Bye.
Our pleasure.
Just add a constant. Everything can be explained.